Today, we're diving into an idea that sounds like it's straight out of a sci-fi novel. Creating solid stuff by, well, manipulating time. But what if the secret isn't about using more power, but about finding just the right rhythm?
So let's just get right to the big question, the one that frames this whole thing. Can we actually make solid objects not from a chunk of metal or wood, but from the seemingly empty air all around us? I know, it sounds impossible, right? But the answer is, well, it's way more interesting than a simple yes or no.
Okay, let's get into it. And we're not going to start with some super abstract high-level theory. Nope. We're starting in the lab with a real, repeatable experiment that people are doing right now. And it's a process for making, and I mean this literally, stone from air.
Now let's get one thing straight right from the get-go. This is not magic. You can't just create atoms out of nothing. All the fundamental laws of physics still apply. This is all about taking the raw materials that are already in the atmosphere and finding a way to assemble them with a totally new kind of efficiency.
So, how does it actually work? Well, the setup is almost simple. You've got a fan that pulls in CO2 from the air, bubbles it through some water that has a calcium source in it. Steps 1, 2, and 4 are pretty standard chemistry. But the secret sauce, the whole breakthrough, it all happens in step 3, applying a precisely patterned energy field. That's the key.
And here is that crucial step in action. On one side, you have the standard way of doing things, just kind of blasting the mix with random energy. But on the other side, you have the breakthrough. It's called the 1/3 hex program. The energy here isn't random at all. It's delivered from 3 different sources that are phase-locked, which just means they're pulsing in a perfect, synchronized, repeating pattern. And here's the absolute kicker. Both methods use the exact same total amount of energy.
And the result of that simple pattern? It's incredible. For the same energy cost, the hex program gives you a higher mass of material. And not just that, the material itself is denser and it's structurally stronger. So this is the whole point. We get a much better result not by throwing more power at the problem, but by adding more information, more order to the power we're already using.
So this leads us to the real mystery, doesn't it? If it's not about how much energy you use, but the pattern of that energy, what's actually going on here? What is the fundamental principle that lets a simple rhythm have such a huge effect on creating matter?
Well, the answer is a really mind-bending concept called time fraction locks. This is the big idea, the theoretical key that explains everything we just saw in that experiment.
So what on earth is a time fraction lock? Okay, think of it like this. Imagine a ripple on a pond that just suddenly freezes in place. It's a stable, repeating pattern or rhythm that locks energy into a structure. And this structure becomes so stable that it starts to act just like a particle. It has the properties that we think of as, solid matter.
And this leads to a really powerful, super elegant conclusion. Matter is just frozen time fractions. It suggests that the solid stuff we see and touch, at its most basic level, is really just a highly organized dance of energy locked into a repeating rhythm.
And it turns out different rhythms, or different fractions, create completely different structures. They're like geometric blueprints. So a 1/2 fraction, that creates polarity, kind of like a particle and its antiparticle. A 1/5 fraction gives you these open, growing spirals. But a 1/3 fraction, that creates perfect closure, a stable hexagonal symmetry.
And that brings us right back to the beginning. The reason the 1/3 hex program works so well in our experiment is because that 1/3 fraction lock is the perfect blueprint for creating a stable, dense hexagonal crystal. We weren't just adding random energy, we were literally telling the molecules exactly how to build themselves.
So now that we have this principle, let's see just how fundamental it really is. Because this isn't just about making better materials in a lab. Oh no, this principle scales across pretty much all of existence on what's called the ladder of creation.
This ladder shows how this one simple rule, time fraction locks, builds our reality from the ground up. It starts with stuff we can actually create in labs today, called quasi-matter, and it climbs all the way up to true particles like protons and neutrons, and it even suggests that the Big Bang itself might have been the very first time fraction lock.
And just to be super clear, that first rung on the ladder, it's not a theory, it's happening. Physicists are creating these quasi-matter things right now. By locking light and magnetic fields into patterns, they create these stable little knots of energy that act just like particles. You know those weird plasma fireballs that last way longer than they should? Turns out they're probably being stabilized by these exact same time fraction locks.
So, here's the really crucial point. The physics creating those strange little plasma fireballs in a lab are the very same rules that created the most fundamental particles in the entire universe.
The scale is completely different, but the blueprint, it's identical.
Let's take the proton, a building block of, well, everything. At the crazy high energies of the early universe or inside a particle collider, you see the same fractions at play. A 1/2 fraction lock creates these fleeting pairs of quarks and antiquarks, but a 1/3 fraction lock? That creates a stable 3-part closure. It locks 3 quarks together to form the stable protons that make up you, me, and everything else.
But, okay, here's the big reality check. While we can use these ideas to template materials like stone with low energy, creating a true particle like a proton from nothing is a whole different ballgame. That requires giga-electron volts, the kind of cosmic energy that you'd only find in the heart of a star or at the exact moment of impact inside a massive particle accelerator.
So if we're not about to build a starship engine with this tomorrow, what's the point? What are the practical, real-world implications of looking at reality this way? What does this mean for us right now?
The key takeaway is really this. We've basically unlocked a new tool for manufacturing. It's not a new chemical, it's not a new power source, it's a new principle, phase geometry. It's the ability to use patterns, not just raw power, to build better, stronger things way more efficiently.
And this isn't some far-off futuristic theory. We're talking about real, tangible applications that are possible today. We can make better stone from the CO2 in the air, we can create superior carbon materials, we can even use nitrogen from the air to make steel harder, all by using these phase-controlled patterns to make old processes work way, way better.
And the benefits they're seeing in experiments are really compelling. Applying phase control isn't just a tiny little tweak, it's a major upgrade. We're talking about reactions that happen faster, materials that are stronger, getting more product out of the same ingredients, all while using less energy. It's literally about working smarter, not harder, but at a molecular level.
And that leaves us with this final, really tantalizing thought. If matter really is just a pattern of energy that's frozen in time, and we're just now learning how to control those patterns, what else can we build? What new materials, what new structures are just sitting there, waiting for us to find the right rhythm, the right frequency, the right lock to bring them into existence?